Universe is overflowing with life. Mathematics proves it, logic confirms it, common sense points to it. Only the cosmos is silent. Absolute, oppressive, frightening silence. Not a single signal in 70 years of searching, not a single confirmation, not a single piece of evidence. Trillions of stars, billions of planets, millions of potentially habitable worlds around us now exist, breathe, live. And everyone is silent. This is not just strange, it is impossible. This contradicts everything we know about probabilities, about time, about the scales of the cosmos. Physicists call this the Fermi Paradox, and I call it the most frightening mystery of humanity. If you are interested in such exciting questions about space and science, be sure to subscribe to the channel and give it a like. It will be even more interesting further, and I will know that you like such content and will continue to explore with you the deepest secrets of the universe. Year 1950. Los Alamos National Laboratory in New Mexico. A group of physicists goes to lunch, an ordinary walk, an ordinary conversation. Nothing special. Scientists are just discussing another comic from the newspaper. In this comic, the artist offered a funny explanation for the strange disappearances of trash cans on the streets of New York. Aliens are kidnapping them. Everyone laughs. Someone jokes about little green men. Someone recalls the latest reports about flying saucers with which the newspapers are full. And suddenly one of the physicists, Enrico Fermi, a Nobel Prize winner, one of the creators of the atomic bomb, stops in the middle of the conversation and asks a question that will turn all astrophysics upside down. Where is everybody? Only 3 words, but these 3 words contain such an abyss that scientists are still trying to answer them. Fermi was not a romantic. He was a mathematician to the core, a person who was used to counting, checking, proving. And when he asked this question, he had already estimated the numbers in his mind. Our galaxy contains hundreds of billions of stars. The age of the Milky Way is more than 13 billion years. Even if a civilization is capable of moving between stars at a speed of only a fraction of a percent of the speed of light, and this is a technology that looks achievable even for us, in the foreseeable future, it would need only a few million years to colonize the entire galaxy. A few million years is an instant by cosmic standards. This is not even seconds on the clock of the universe. This is less than the time of existence of dinosaurs on Earth. This means if at least one civilization in the Milky Way ever reached a technological level allowing interstellar flights, only one in the entire history of the galaxy, it should have settled everywhere millions of years ago. Their ships should have arrived on Earth even when trilobites were swimming here. Their stations should have been hanging over every star. Their tracks should have been everywhere, but they are not. No tracks, no signals, no artifacts, no one. Fermi's colleagues at first treated the question lightly. One of them suggested that interstellar travel is simply impossible. Another said that civilizations are too rare. A third noted that the distances are too great. No, Fermi continued to insist. He broke the problem into parts like a mathematical problem. Look, he said, the sun is an ordinary star. The Earth is an ordinary planet. We are an ordinary result of the evolution of carbon life. Nothing unique, nothing special. The Copernicus principle, one of the foundations of modern science, tells us exactly this. We are not the center of the universe. We are not special. We are one of many. If this is so, then intelligent life must arise constantly. Let it not be on every planet, let it not be in every system, but with such a number of stars, with such time, with such a universe, there must be millions of them. Where are they? Over lunch, the physicists did not come to an answer. But the question remained. It stuck in minds. It spread through the scientific community. It became an obsession for astrophysicists, biologists, philosophers. The Fermi Paradox, as it was called later. The paradox of the great silence. Contradictions between theory and reality, between mathematics of hope and physics of loneliness, between what should be and what is. And the more we learned about space, the deeper this paradox became. Every new discovery made the silence of the universe even more mysterious. Every new telescope, every new mission, every new observation only strengthened the question, where is everybody? It is interesting that Fermi himself, according to eyewitness accounts, did not formulate the paradox in the form in which we know it now. He simply asked questions and expressed doubts about the possibility of interstellar flights. A full formulation of the paradox was given by another scientist, astronomer Michael Hart, only in 1975. Hart reasoned harshly and uncompromisingly. He said, "The very absence of aliens on Earth right now is convincing evidence that highly developed civilizations simply do not exist, because if they existed, they would have been here long ago." Even taking into account that interstellar flights are difficult, even taking into account that civilizations develop slowly, there was more than enough time. The galaxy is billions of years old. If a civilization began expansion at least 1 billion years ago, it would have had time to reach every star, and they are not visible anywhere. Therefore, Hart concluded, probably we are alone, at least in our part of the universe. But there is a nuance. Absence of evidence is not evidence of absence. Perhaps they are, but we just do not see them. It is quite likely they were here long ago, when we were not yet here. It is not excluded that they will come tomorrow. They can hide or remain silent intentionally, or use technologies that we do not understand, or speak in a language that we do not hear. There turned out to be many variants of explanation, and each of them generates new questions, new mysteries, new fears. Well, let us start with numbers. Let us look at the numbers that turn the silence of space into a real disaster for logic. Imagine the Milky Way, a spiral galaxy, diameter about 100,000 light-years, disk thickness about 1,000 light-years in the center, mass approximately 1.5 trillion times greater than the mass of our Sun. And in this giant whirlpool of stars, gas, and dust, there are from 200 to 400 billion stars. We do not know the exact number. Many stars are too dim to be seen. Many are hidden behind clouds of interstellar dust. But even if we take the lower estimate of 200 billion, this number is so huge that our brain cannot truly grasp it. If you started counting these stars aloud one by one per second, not stopping for a moment, you would need more than 6,000 years to count to the end. 6,000 years is the entire history of human civilization from the first cities to our days. And now add another fact here. We live in an era of revolution in astronomy. In the 1990s, when I was not yet born, we knew about the existence of only a few planets outside the solar system. Today, we know about more than 5,000 exoplanets, 5,000 confirmed worlds around other stars. And this is only the beginning. The Kepler Space Telescope, which worked until 2018, showed us a striking thing. Planets are the norm, not an exception. Practically every star has planets. Some have 1, some a dozen. On average, several planets per star. In other words, in our galaxy, there are more than 1 trillion planets. 1 trillion, 1 with 12 zeros. 1,000 billion worlds. And this is only in the Milky Way. And there are about 200 billion galaxies in the observable universe. But another discovery is even more important. It turned out that Earth-type planets, rocky worlds where liquid water can potentially exist, are not such a rarity. According to astronomers' estimates, approximately every 5th Sun-type star has a planet in the so-called habitable zone, at that distance from the star where the temperature allows water to remain liquid. In our galaxy alone, these are tens of billions of potentially habitable planets, tens of billions of places where life can theoretically arise. And this is only planets at Sun-type stars. But there are also red dwarfs, stars of which there are many more in the galaxy than Sun-like ones. Their habitable zone is located closer to the star, but it exists. There are data that planets with liquid water can exist there too. Now let us add the time factor. The universe is about 14 billion years old. The Milky Way is more than 13 billion. The first stars and planets began to form very early. Our Earth was formed 4.5 billion years ago, but the universe by that moment had already existed for 9 billion years. Consequently, there could be planets and civilizations that appeared billions of years before us. Imagine a civilization that arose only a billion years before humanity, a billion years of technological development, a billion years of evolution, a billion years of science, research, expansion. We cannot even imagine what technologies they could possess. For them, our rockets would be more primitive than stone axes, our computers simpler than counting sticks. They could rebuild stars, create artificial planets, travel between galaxies, manage space and time, and possibly even something that we cannot think of. And this is where the most terrible thing begins. With such numbers, with such scales, with such time, the absence of at least some traces of intelligent life looks not just strange, it looks impossible. Statistically, mathematically, logically impossible, if we take the most conservative estimates. If we assume that life arises extremely rarely, that intelligent life is even rarer, that technological civilizations are exceptions of exceptions, even then there should be thousands of them. Thousands of civilizations in our galaxy right now and tens of thousands that existed in the past. Some of them should have developed to the level of interstellar flights. At least some, at least one. And this one should have spread throughout the galaxy. Their probes should have been in Earth's orbit. Their signals should have filled the radio airwaves. Their megastructures should have been visible in our telescopes. Where are they? Why is the cosmos silent? This is the Fermi Paradox in its full, terrifying beauty. The universe should be teeming with life. Mathematics guarantees it. But all our observations say the opposite. We are alone, absolutely, completely, totally alone in the observable part of space. And this discrepancy, this gap between expectation and reality, is so huge that it requires an explanation, a radical explanation. An explanation that will either turn our understanding of life upside down or turn our understanding of the universe upside down. Either we fundamentally misunderstand how life arises and develops, or we fundamentally misunderstand the laws of physics and the possibilities of technologies, or something else is happening, something that we do not even guess. And this last one is the most frightening. But we are getting ahead of ourselves. Let us first see how scientists tried to turn Fermi's intuitive feeling into precise mathematics, how they tried to calculate the probability that we are not alone, and why these calculations only exacerbated the paradox. In 1961, astronomer Frank Drake organized the first conference dedicated to the search for extraterrestrial intelligence. He invited a group of scientists, astronomers, physicists, biologists to discuss one question. How many civilizations in our galaxy are capable of entering into contact with us right now? Preparing for the meeting, Drake sketched a formula on the board. Simple in appearance but revolutionary in essence, he broke a big question into several small factors. Each factor could be assessed separately and then multiplied and get an answer. This formula went down in history as the Drake equation, and it became simultaneously a beacon of hope and a source of despair for all who search for brothers in mind. Here is what the Drake equation looks like in its classical form. The number of civilizations is equal to the product of 7 multipliers. The first multiplier is the rate of star formation in our galaxy. How many new stars are born every year? The second is the fraction of stars having planets. The third is the average number of planets in a system where conditions are suitable for life. The fourth is the fraction of planets where life actually originates. The fifth is the fraction of planets where life develops to intelligent forms. The sixth is the fraction of civilizations that develop technologies capable of interstellar communication and want to do it. The seventh is the average time of existence of such a civilization, the time during which it sends signals into space. When Drake first wrote down this equation, most parameters were pure guesses. He substituted values into the formula that seemed reasonable. The star formation rate is 10 new stars per year. Half of them have planets. On average, 2 planets per system are in the habitable zone. On all planets where it is possible, life necessarily arises, but only 1% of life develops to intelligent forms. And only 1% of civilizations develop communication technologies. The average time of existence of a technological civilization is 10,000 years. Multiply all this, and you get 10. 10 civilizations in our galaxy right now are ready to communicate with us. Sounds encouraging, right? We are not alone. There are 10 of them. Somewhere out there, among the stars, there are 10 worlds where intelligent beings look at the sky and ask themselves the same question as we do. But there is a problem, a huge fundamental problem with the Drake equation. We still do not know most of its parameters. We can only guess them. The first 2 parameters, the star formation rate and the fraction of stars with planets, we now know quite accurately. Modern astronomy has given us these numbers. It turned out that stars with planets are almost 100%. This is good news. The third parameter, the number of planets in the habitable zone, also became clearer thanks to missions to search for exoplanets. Approximately every 5th Sun-type star has a planet in the right place. But then, the unknown begins. The fourth parameter is the probability of the origin of life, a complete mystery. We know only one example, the Earth. Life on our planet arose strikingly quickly. Literally, as soon as conditions became more or less suitable, about 3.5 billion years ago, the first microorganisms already appeared. This can mean that life arises easily, that it is a natural process that happens everywhere where there are suitable conditions. Water, energy, chemistry, and life is inevitable. Or not, perhaps we are just incredibly lucky. Suppose life on Earth is the result of 1 million incredible coincidences. Chains of events are so improbable that it was not repeated anywhere else in the universe. We do not know. We do not have statistics. One example is not statistics. It is an anecdote. Therefore, the fourth parameter in the Drake equation can be estimated anywhere from practically 1 to practically 0, and everything depends on this choice. The fifth parameter is even worse, the probability of the development of intelligence. Life on Earth has existed for almost 4 billion years. Intelligent life for several 100,000 years. Consequently, the path from bacteria to humans took a huge amount of time and passed through countless accidents. The extinction of dinosaurs, the exit to land, the appearance of an oxygen atmosphere. Each of these steps might not have happened or happened differently. Intelligence is not an inevitable result of evolution. It is one of the possible results. And how probable it is, we do not have the slightest idea. The sixth parameter. A technological civilization wishing to communicate is even more foggy. Humanity has possessed radio technologies for a little over 100 years. This is a tiny period of time. We actively sent signals into space for only a few decades, then mostly switched to receiving. Moreover, our own civilization is already moving toward technologies that almost do not radiate into space. Directional transmissions, fiber optics, cable networks. Our planet is becoming quieter in terms of radio emission, not louder. It is quite likely that technological civilizations have a very short contact window. Polish science fiction writer Stanislaw Lem suggested that this window might be only 300 to 500 years. A civilization transitions from a pre-industrial society to a post-industrial one so quickly that it simply does not have time to make noise in the radio range long enough. And finally, the seventh parameter, the lifespan of a civilization, the most sinister of all. Drake optimistically suggested 10,000 years. Carl Sagan, The great popularizer of science and one of the inspirers of the program to search for extraterrestrial intelligence believed that this parameter was critical. All other factors in the equation may be quite high, but if civilizations are prone to self-destruction, if they discover nuclear energy, biological weapons, artificial intelligence, and then use these technologies to wipe themselves off the face of the planet, then the average lifespan of a civilization can be very short. 100 years, 50 years, or even less. And then in the Drake equation, all other beautiful large numbers are multiplied by an insignificantly small value, and the result becomes close to zero. That is the trickery of the Drake equation. It looks like a scientific tool, like a way to get a numerical answer to the question of extraterrestrial civilizations. But in reality, it is a mirror of our hopes and fears. If you are an optimist and believe that life arises easily, intelligence develops easily, and civilizations live long, you will get thousands and millions of civilizations in the galaxy. If you are a pessimist and believe that each of these steps is extremely unlikely, you will get zero. We are alone. The Drake equation does not solve the Fermi paradox. It formalizes it, turns an intuitive feeling into a mathematical problem. It shows us exactly what we do not know and how huge these gaps in our knowledge are. One of the critics of the equation, science fiction writer Michael Crichton, in 2003 said harshly and directly, "The Drake equation is absolutely meaningless and has nothing to do with science. Science creates verifiable hypotheses, and the Drake equation is based on parameters that we cannot verify and will not be able to for a very long time. This is not a tool of knowledge, it is a form of organized ignorance." The criticism is sharp, but in some ways fair. We cannot substitute the correct numbers into the equation, so we substitute guesses and get results that say more about ourselves than about the universe. Nevertheless, the Drake equation did an incredibly important thing. It showed that the question of extraterrestrial civilizations can be investigated scientifically, can be broken into parts, can be studied. And most importantly, it showed exactly what knowledge we need, what research to conduct, what observations to make, what experiments to set. And then the next question arises, what if there is no Fermi paradox at all? Suppose the explanation is simple. Civilizations are so rare that we really are the only ones in the observable part of the universe. Suppose some of the parameters of the Drake equation are actually practically equal to zero, and therefore the cosmos is silent. This idea led to the emergence of one of the most frightening hypotheses in the history of science. A hypothesis that explains the silence of the cosmos, not by the fact that there are few civilizations, but by the fact that there is something that does not allow them to survive long enough. A filter, a barrier, a wall against which all attempts of life to reach the stars are broken. In 1996, economist Robin Hanson published an essay with the gloomy title, "The Great Filter is Almost Behind Us." In it, he proposed a radical solution to the Fermi paradox. Imagine, Hanson said, that on the path from inanimate matter to an interstellar civilization, there exists one or several stages to overcome which is extremely difficult. So difficult that the overwhelming majority of attempts fail. This is the great filter, a barrier that weeds out almost all contenders, which ensures that even in a huge universe, even with billions of chances, intelligent life remains a rarity. Not because the laws of physics or biology are somehow particularly unfavorable, but because somewhere on this path there exists an almost insurmountable obstacle. Hanson compiled a list of stages that a civilization must pass from origin to a flourishing of cosmic scale. The first stage is the formation of a planetary system with habitable conditions: the right star, the right orbit, the right chemical composition. The second is the appearance of self-replicating molecules, what we call the origin of life, the transition from chemistry to biology. The third, the appearance of cells with a nucleus, eukaryotes. On Earth, this took almost 2 billion years. The fourth, multicellularity, organisms consisting not of one cell, but of millions. The fifth, sexual reproduction, which sharply accelerates evolution. The sixth, organisms with complex organs and systems, animals. The seventh, intelligence, the ability for abstract thinking, for planning, for culture. The eighth, a technological civilization capable of changing the planet. The ninth, interstellar expansion, spreading beyond the home planet, colonization of other worlds. Somewhere on this path, Hansen argues, is the Great Filter, a stage so complex that only units out of millions or billions of attempts pass it. And now the most important thing. Where exactly is this filter located? In the past or in the future? Behind us or ahead? This is not an idle question. The fate of humanity depends on the answer to it. If the Great Filter is behind us, if we have already overcome the most difficult barrier, this is good news, wonderful news. It means the path to the stars is open, the hardest part is past. Our chances of becoming an interstellar civilization are high. We are likely unique in the galaxy. Perhaps we are the first. Suppose the entire universe is waiting for us, empty and ready for colonization, lonely, but ours. What could be better? And if the Great Filter is ahead? If the hardest part is yet to come, then it is a disaster. Then something stands in our way that destroys almost all civilizations. Something so deadly, so inevitable, that it is practically impossible to avoid it. And we are heading towards this, blindly, not knowing what awaits us. Perhaps it is a nuclear war, or an ecological collapse, or artificial intelligence that will get out of control, or some technology that we have not yet discovered, but which will inevitably lead to self-destruction, or in general something that we do not yet guess. A cosmic danger, a physical law, a biological inevitability, something that awaits all civilizations that have reached a certain level of development. That is why the question of the location of the Great Filter is a matter of life and death, not metaphorically, but literally the life and death of the human species. And here a sinister paradox arises. The more we find evidence that life in the universe is widespread, the worse it is for us. Every new planet in the habitable zone, every discovery of complex organic molecules in space, every hint that life arises easily is bad news. Because if life is common, if intelligence is not a rarity, if civilizations arise constantly, but the cosmos is still silent, then the filter is ahead. Something kills everyone. We are next. Imagine that tomorrow we find life on Mars, not just organic molecules, not just traces of water, but real life. Bacteria, microorganisms, even if they died out millions of years ago, but unambiguously biological. This will be the greatest discovery in human history. We will learn that life is not unique to Earth, that it can arise independently in different places, that the universe is full of life. But from the point of view of the Great Filter hypothesis, this is terrible news, because then the early stages of the origin of life, the evolution of simple organisms, are passed relatively easily. The filter is not there. The filter is further, probably at the stage of intelligence, or at the stage of technology, or at the stage of going into space. And we have not reached it yet. It is still ahead. And now imagine another scenario. We explore the entire solar system. Mars, the moons of Jupiter, the moons of Saturn, Pluto, the Kuiper Belt, everywhere where life could theoretically exist. And we find nothing. Absolutely nothing. No microbes, no organics, no traces. Earth is unique even within our system. On the one hand, this is a disappointment. We are alone even here, in our small corner. But from the point of view of the Great Filter, this is good news, wonderful news. It means the filter is somewhere in the early stages. Probably the origin of life is extremely rare, or the transition to eukaryotes is almost impossible, or the appearance of multicellularity is incredible luck. But since we have already passed these stages, since we are here, intelligent and technological, The hardest part is behind. Our chances of surviving and flourishing are quite high. Do you see the irony? The more lonely we turn out to be, the better it is for us. The more evidence that the universe is dead, the higher our chances of survival. And every new piece of evidence in favor of the prevalence of life is another nail in our coffin lid. The Great Filter Hypothesis is one of the darkest ideas in the history of science. It turns the search for extraterrestrial life into Russian roulette. Every discovery is a pull of the trigger, and we do not know in which chamber the bullet is, but we know that with every pull, the probability of a shot grows. Hansen does not say where exactly the Great Filter is. He only shows the logic, explains why the silence of the cosmos is so important, why the absence of aliens is not just a mystery, it is a message, a warning, a sign that somewhere on the way to the stars there exists a deadly danger, and our task is to understand where it is. Whether we have passed it or not, because the future of humanity depends on this. And one more point that makes everything even darker. The Great Filter does not necessarily have to be one thing. It could be a series of barriers, several critical points, each of which weeds out most of the contenders. Suppose the origin of life is already a fairly rare event. Then the development of intelligence weeds out even more. Then a technological civilization, another barrier, and then finally some last filter that almost no one passes. A chain of low probabilities, and we are somewhere in the middle, not knowing how many more trials are ahead. But there is another option. Probably the problem is not that life is rare or that civilizations perish. Suppose the problem is in how the universe itself is structured, in the conditions that are required for the emergence and development of complex life. Perhaps we really are unique, not because of incredible luck, but because of incredibly specific requirements. It is not excluded that Earth is not one of millions of examples of a suitable planet, but a single instance in the entire galaxy, or even in all of nearby space. And if this is so, if we live on a planet that is so special that there are simply no analogs to it, then the silence of the universe receives a simple explanation. There is no one, because the conditions for life are so specific that they simply are not repeated anywhere else. This idea became the basis for another hypothesis that we will now consider. A hypothesis that asserts Earth is not just a rarity, she is unique. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published a book with the provocative title, Rare Earth: Why Complex Life is Uncommon in the Universe. In it, they collected all the data known at that time about what factors are necessary for the emergence and maintenance of complex life. And they came to a surprising conclusion. The list of requirements is so long and specific that the probability of repeating the conditions of Earth anywhere else becomes insignificantly small. Not zero, but so close to zero that in practice we may turn out to be the only planet with complex life in the observable part of the universe. Let us look at these requirements. Let us start with the star. We need a star of a certain type, not too hot. Such stars quickly burn their fuel and explode, not giving life time to develop. Not too cold. Around such stars, the habitable zone is too narrow, and planets there will be tidally locked, always turned to the star with one side. The Sun is a G-class star, perfectly suitable, but there are only 5% of such stars in the galaxy. Most stars are red dwarfs, which live for trillions of years but constantly produce powerful flares that sterilize the surface of nearby planets. So the first limitation is that the star must be of the right type. This immediately removes 95% of stars from consideration. Now the planet. The orbit must be almost circular. If the orbit is highly elongated, the planet will alternately freeze and overheat. Each year, life will not have time to adapt. Earth moves in an almost perfect circle. The deviation is minimal. The planet must be at the right distance from the star. Too close and the water will evaporate, too far and it will freeze. This zone is called habitable, and it is quite narrow. Earth is located almost in the center of this zone, an ideal place. The mass of the planet is also important. Too small, it will not hold an atmosphere. Gravity is weak, gases will fly off into space. Too large, the atmosphere will become monstrously dense. Pressure will crush any life. Earth has a mass somewhere in the middle. The right gravity, the right atmosphere, but this is only the beginning. The planet must have a magnetic field. A powerful, stable magnetic field that protects the surface from the solar wind and cosmic rays. Earth has such a field thanks to a liquid iron core that rotates and creates a dynamo effect. Mars once had a magnetic field, but it disappeared, and the solar wind stripped most of the atmosphere from the planet. Without protection, radiation sterilizes the surface. The planet must rotate at the right speed. Too slowly, and one side will forever be turned to the star, like the moon to the Earth, creating extreme temperature contrasts. Too quickly, constant hurricanes, an impossible climate. Earth makes a revolution in 24 hours, an ideal rhythm of day and night. The axial tilt is also critical. Without a tilt, there will be no change of seasons. The climate will become monotonous. Too large a tilt, and seasonal changes will be catastrophic. Earth has a tilt of about 23 degrees, creates moderate seasons. The diversity of climatic zones stimulates evolution. And now the most interesting part, the moon. Our satellite plays the role of a stabilizer. Without the moon, the axis of Earth's rotation would be unstable. The planet would tumble, the tilt would change chaotically, the climate would jump from one extreme to another. Life could not develop in such conditions. The moon holds the axis of the Earth, makes our climate predictable for millions of years. Moreover, the moon creates tides. Tides mix the oceans, transport nutrients, create zones between land and water where life could first come ashore. Tides could have been a critical factor in evolution. And where did the moon come from? A popular hypothesis says that 4.5 billion years ago, a planet the size of Mars crashed into the young Earth. The collision was at a certain angle with a certain speed. The moon was formed from the material ejected into space. This is an incredibly rare event, a coincidence of cosmic scale. Let us go further. The planet must have plate tectonics. The movement of continental plates is critically important for maintaining life. Plates recycle the crust, return carbon from the atmosphere back to the interior, regulate the climate on geological timescales. Without tectonics, the planet would turn into either an ice ball or a red-hot furnace. Venus, for example, does not have plate tectonics, and this is one of the reasons why the surface temperature there reaches hundreds of degrees. Earth is active, plates move, mountains grow, oceans push apart, volcanoes erupt. This activity creates a variety of conditions, stimulates evolution, maintains balance. The planet must have enough water, but not too much. Too little, and it is an arid desert. Too much, and the ocean will cover the entire surface. There will be no land, no diversity of ecosystems. Earth has an ideal ratio, about a third land, 2/3 water. It creates continents, islands, coasts, diversity of climatic zones. Location in the galaxy also matters. Earth is at a distance of about 27,000 light-years from the center of the Milky Way. Not too close. In the center of the galaxy, there is a high concentration of stars, frequent supernova flares, powerful radiation from the central black hole. Life there would be constantly under the threat of sterilization. Not too far. On the outskirts of the galaxy, there are few heavy elements from which Earth-type planets and life itself are formed. We are in the so-called galactic habitable zone. Moreover, our orbit around the center of the galaxy is almost circular and synchronized with the spiral arms. We spend most of our time between the arms, where there are fewer dangerous cosmic events. Again, the right place at the right time. The atmosphere must have the right composition. Enough oxygen for complex life, but not too much. Otherwise, everything will constantly burn. Enough nitrogen for stability. carbon dioxide in the right proportions for the greenhouse effect, and the ozone layer for protection from ultraviolet light. On Earth, all these components are balanced. Moreover, this balance is maintained by life itself. Plants produce oxygen, bacteria regulate the nitrogen cycle, oceans absorb carbon dioxide. The system is self-regulating, but to start it, the right initial conditions were needed. The planet must have enough heavy elements: carbon, oxygen, iron, phosphorus, nitrogen. All these elements are necessary for life, and they are all created only in the interiors of stars and during supernova explosions. Earth is rich in these elements because it was formed from the material of several generations of stars. We are literally made of stardust. But for this, the solar system had to be born at the right time. Not too early, when heavy elements were not yet there, not too late, when star formation slowed down. Ward and Brownlee compiled a list of more than 100 conditions that must be met simultaneously for the emergence and maintenance of complex life. And each of these conditions reduces the probability. Every new requirement makes planets similar to Earth even rarer. Multiply all these probabilities and you get a number so close to zero that practically we may be the only planet with complex life in the observable part of the universe. Not because life is impossible, but because the requirements are so specific that they simply are not repeated anywhere else. The rare Earth hypothesis explains the Fermi Paradox simply and elegantly. We do not see aliens because they are not there. We are alone not because of a filter that kills civilizations, but because civilizations simply do not arise. Conditions are too specific. Coincidences are too incredible. Of course, this hypothesis has critics. Many scientists consider it too anthropocentric, too narrow. We know only one type of life: terrestrial. Carbon chemistry, water as a solvent, oxygen for breathing. But who said that this is the only possible option? Perhaps life based on silicon instead of carbon, or liquid methane instead of water, like on Titan, the moon of Saturn, or organisms breathing hydrogen or methane, or life in the clouds of gas giants, or in the underground oceans of icy moons, or even in interstellar clouds. We just do not know what forms life can take. Limiting the search only to planets similar to Earth, we may be missing millions of other worlds where life exists, but in forms that we cannot recognize. Carbon chauvinism. That is what critics call this narrowness of thinking. But even if we set aside these objections, the rare Earth hypothesis leaves an important question. Okay, we are unique. We are alone in the galaxy, perhaps even in the local group of galaxies. But should we rejoice at this or be horrified? On the one hand, the entire galaxy belongs to us. Billions of stars await colonization. We can settle, grow, build an empire of stellar scale. No one will interfere, no one is competing for resources. The future of humanity is boundless. On the other hand, what a responsibility it is. We are the only carriers of intelligence in this part of the universe. The only ones who can know the cosmos, ask questions, seek meaning. If we destroy ourselves with war, ecological disaster, technological suicide, intelligence will disappear from this corner of space, probably forever or for billions of years, until the same incredible conditions accidentally align again somewhere else. To be the only ones is the greatest privilege and the greatest curse at the same time. But what if the reason for the silence of the cosmos is not at all in the rarity of life? What if civilizations exist, there are many of them, but they all remain silent intentionally? What if the universe is not an empty arena, but a dark forest full of hunters, where anyone who gives away their presence risks being destroyed? This idea was born in science fiction, but quickly migrated into serious scientific discussions, and it scares more than any other hypothesis. Chinese science fiction writer Liu Cixin, in the novel The Dark Forest, proposed a sinister explanation for the Fermi Paradox. Imagine, he says, that the universe is a huge dark forest. Every civilization is a hunter with a weapon. creeping between the trees. The hunter knows two things. First, survival is the top priority for any form of life. Second, it is impossible to know for sure the intention of another hunter. You meet someone in a forest. They might be friendly or aggressive or weaker than you now, but stronger tomorrow. You cannot communicate with them effectively. The distance is vast, signals take years, and cultures are incomprehensible to each other. You cannot trust them because even if they are not a threat now, technologies develop exponentially. And what is a weak, primitive civilization today may become an invincible force tomorrow. What do you do in such a situation? The logic of game theory is ironclad. The safest option is to fire first, to destroy the other civilization before it becomes a threat, before it destroys you. Sixon describes this through a simple chain of reasoning. The first axiom, survival is the primary need of a civilization. The second axiom, civilizations constantly grow and expand, but the amount of matter in the universe is finite. From this it follows, resources are limited, competition is inevitable. The third axiom, it is impossible to determine the true intentions of another civilization due to vast distances, cultural differences, and communication delays. The fourth axiom, technological progress is unpredictable and follows an exponential curve. A weak civilization today may make a breakthrough tomorrow and become a dominant force. From all this it follows, if civilization A learns of the existence of civilization B, the most rational action for A is to immediately destroy B because waiting is risky, communication is unreliable, and a technological explosion could flip the balance of power at any moment. It is better to kill now than be killed later. This is called a chain of suspicion. I do not know if you are hostile or not. Even if you say you are friendly, I cannot believe you. You might be lying. Even if you are not lying now, you might change your mind later. Even if you do not change your mind, your descendants might be different. Even if your civilization is stable and peace-loving, I cannot verify this without risk. Therefore, the only guarantee of safety is your destruction. And you think the same about me. Therefore, we both remain silent, hide, and try not to leave tracks. Because in a dark forest, any sound, any light, any movement can attract a predator, and the one who gives themselves away first dies first. That is why the cosmos is silent. Not because there are no civilizations, but because everyone who is smart enough to survive is smart enough to remain silent. The dark forest theory explains not only the absence of signals, but also the absence of colonization. Why has no one settled across the galaxy? Because expansion attracts attention. Every new colony is a beacon screaming into space. We are here, we are growing, we are becoming stronger, and other civilizations, seeing this, strike immediately. Therefore, it is safer to remain quiet, small, and invisible, to develop slowly, and not to stick one's head out. It is quite likely that civilizations exist for millennia, but never move beyond their planetary systems because they know it is suicide. In this picture of the universe, humanity is making a monstrous mistake. We have been sending radio signals into space since the 1970s. We sent probes with information about our location. We build powerful radio telescopes and actively shout, "We are here! Hello! Is anyone alive?" And every such signal is an invitation to our destruction. A foolish child walking through a dark forest with a flashlight and shouts, attracting the attention of hunters. Some scientists take the dark forest theory seriously. Physicist Stephen Hawking warned that attempts to establish contact with extraterrestrial civilizations could be dangerous. He compared it to the meeting of Native Americans with Columbus. Not the most successful contact for the indigenous inhabitants. If a highly developed civilization finds us, Hawking said, it might view Earth simply as a source of resources. Our interests, our lives, would be no more important to them than bacteria in a petri dish are important to a scientist. Destroy, colonize, use. Therefore, perhaps the best strategy for humanity is to maintain radio silence, stop sending signals, become invisible, lie low, and wait, developing quietly until we become strong enough to protect ourselves, if we ever do. But there is a problem with the dark forest theory. It assumes that all civilizations think the same way, that all follow the same logic of fear and suspicion, and that there is not a single civilization that would choose a different path. But why? On Earth, cultures are different. Some societies are more aggressive, others more peaceful. Some isolate themselves, others actively seek contact. Why should it be different in space? Astrophysicist Moya McTeer rightly notes, "We do not see such uniform behavior even on Earth. Somewhere there is fear, somewhere curiosity, somewhere aggression, somewhere cooperation. It is unlikely that all civilizations in the universe follow one strategy. There must be exceptions. There must be those who chose the path of openness. And if at least one of thousands of civilizations decided not to hide, we should have seen its signals, but we do not see them. So the dark forest theory is either incomplete or something else is happening. Moreover, technically it is almost impossible to hide. Any developed civilization produces heat. Industry, cities, power stations, transport, all of this radiates in the infrared range. It is impossible to camouflage a planetary civilization. Its thermal signature will be visible in any sufficiently powerful telescope. If a civilization builds megastructures, Dyson spheres around stars, rings around planets, space stations, they will be visible in the optical and infrared range. Radio signals can be stopped, but you cannot cheat physics. Entropy requires the radiation of heat, so if civilizations are hiding, they must remain at a very low technological level, not build anything large-scale, not use significant energy, and effectively freeze in development. But this contradicts the second axiom of the dark forest theory. Civilizations grow and expand, so something in this logic does not add up. Nevertheless, the dark forest theory remains one of the darkest and most fascinating hypotheses. It offers an image of a universe full of intelligence, but an intelligence frozen by fear. Thousands of civilizations hiding in the dark, afraid of each other, incapable of communication. A cosmic prison of suspicion. Everyone is alone, everyone is scared, everyone is ready to kill at the slightest threat. Life exists, but contact is impossible. Not because of distances, not because of technologies, but because of fear. A fear that is more rational than the love of knowledge. But there is another scenario. Civilizations exist. They do not hide, they do not kill each other, but they simply do not want to communicate with us. Not out of fear, but out of ethics, out of respect, out of a desire not to interfere in our development. This idea lies at the basis of another popular hypothesis, the zoo hypothesis. Imagine that a highly developed civilization discovered Earth thousands or millions of years ago. They studied us, realized that intelligent life is developing here, and made the decision not to interfere, not to contact, but to observe from afar, as scientists observe animals in a nature reserve or a zoo, not interfering, not influencing, not revealing their presence. Why? Perhaps they have an ethical code, something like the Prime Directive from Star Trek, the principle of non-interference in the development of less developed civilizations. They understand that contact could be destructive for us psychologically, socially, and culturally. Learning about the existence of highly developed aliens, humanity might lose the motivation to develop. Why invent something if they already know everything? Why explore space if they have already mastered it? Why solve problems independently if one can just ask for help? Or contact could cause social collapse. Religions will fall, faced with proof of the existence of other intelligent beings. Political systems will destabilize. Economies will collapse from technologies that make many professions unnecessary. Panic, chaos, wars for the right of first contact. A civilization might not withstand the shock. Therefore, more rational and ethical aliens decide to wait. Let humanity develop naturally. Let it solve its own problems. Let it mature. And when we reach a certain technological, social, and spiritual level, they will reveal themselves, establish contact, and accept us into the galactic community. But not earlier, and not while we are not ready. In this scenario, Earth is a nature reserve, a protected territory. They know about us. They watch us, probably even visit secretly. Hence all these stories about UFOs and abductions. But there will be no official contact until we pass some test of maturity. This hypothesis was first formulated by American astronomer John Ball in 1973. But even earlier, in 1933, Konstantin Tsiolkovsky wrote about a similar idea in the note. Planets are inhabited by living beings. He pondered why we do not see traces of highly developed civilizations and suggested perhaps they do not want to disturb us, do not want to harm our natural development, and are waiting for us to grow to a level that allows for equal communication. The zoo hypothesis is beautiful and encouraging. We are not alone, but they are wise and patient. They do not interfere out of respect for us, out of an understanding that every civilization must pass its own path independently. And when we are ready, when we overcome wars, inequalities, and ecological crises, when we learn to live in peace with ourselves, then they will say, "Welcome. We have been waiting for you. Now you are part of something greater." But there are serious problems with this hypothesis. First, it requires coordination. If thousands of civilizations exist, how did they all agree to remain silent? How did they agree on the rules of non-interference? This assumes the existence of some galactic federation, a council, a governing body, a mega-civilization that monitors compliance with the rules. But if such a structure exists, it must leave traces, huge, noticeable traces. Interstellar infrastructure, energy consumption on a stellar scale, the movement of fleets between systems. We should have seen this, but we do not. The second problem, one violator is enough. If even one civilization out of thousands decides not to follow the rules, if even one wants to establish contact or colonize or simply become famous as discoverers, the system will collapse. It is impossible to force everyone to remain silent. There will always be those who break the contract. But we see no one. Absolutely no one. The third problem is the assumption of the uniformity of ethics. Why should all highly developed civilizations follow the same moral principles? On Earth, even within one civilization, morality is different. Some cultures value individuality, others collectivism. Some believe in non-interference, others in active assistance. Some consider animals a resource, others as beings deserving protection. Why should it be simpler in space? Why should millions of civilizations with different histories, different biologies, and different evolutions come to the same conclusions about how to treat less developed species? The probability of this is extremely small. And finally, the fourth problem. The longer we do not find traces of civilizations, the less likely the zoo hypothesis becomes. A recent study showed that if we continue the search and do not detect any techno-signatures, any signs of technological activity in the observable cosmos, then we will have to conclude that intelligent technological life is indeed rare. The zoo hypothesis becomes simply a way to delay the recognition of the obvious. We are alone. Nevertheless, the zoo hypothesis gives hope. It says, "Do not despair." The silence of the cosmos does not mean emptiness. It can mean patience, respect, and the wisdom of those who have already passed the path we are only beginning. And our task is to become worthy of contact, to solve our problems, to unite, and to grow. And then, suppose the heavens will open, and we will hear a voice. We are here. We have always been here. We were just waiting for you to be ready. A beautiful thought, comforting, but unfortunately, probably incorrect. There is another explanation for the silence of the cosmos that requires neither filters, nor the uniqueness of Earth, nor a dark forest, nor zoos. An explanation so simple and obvious that we often miss it. Probably the problem is in physics itself, in the laws of the universe, in limitations that make interstellar communication and colonization not forbidden, but simply incredibly difficult. So difficult that almost no one overcomes these barriers. Let us start with distances. The star nearest to the Sun, Proxima Centauri, is at a distance of a little more than 4 light years. It does not sound that scary, right? Only 4 years at the speed of light. The problem is that we cannot move at the speed of light, not even close. The fastest spacecraft that humanity has ever launched, the Parker probe studying the Sun, moves at a speed of about 190 kilometers per second at the moment of maximum approach to the star. This is approximately 0.06% of the speed of light. It sounds fast, but in reality, it is a snail's pace by cosmic standards. At such a speed, the path to Proxima Centauri will take more than 20,000 years. 20,000 years is the time from the Stone Age to our days. The entire history of human civilization packed into one interstellar flight, and that is to the nearest star. Most interesting stars are much further away. The average star in our part of the galaxy is at a distance of several dozen light years. That is hundreds of thousands of years of flight with modern technologies. Fine, you say, but technologies develop, and we will build faster ships, nuclear engines, antimatter, solar sails. Suppose even the most optimistic projects for interstellar ships suggest a speed of no more than 10 to 20% of the speed of light. That is already an achievement. At such a speed, one can reach Proxima Centauri in 40 years. Acceptable for one generation of people, but 10% of the speed of light is an incredible speed. That is 30,000 kilometers per second. At such a speed, a collision with a dust particle releases the energy of an explosion. Cosmic dust, with which interstellar space is full, becomes a deadly weapon. Every particle is a projectile. The ship's protection must be fantastic. Energy consumption colossal. We are talking about energy comparable to the annual energy production of an entire planet just to accelerate one ship. And now imagine that you sent a ship to another star. 40 years on the way, and you arrive. What next? Establish communication with home. The signal takes 4 years one way, 8 years for a question and answer. Conversation in real time is impossible. Every decision the crew must make independently. No help, no consultations with Earth, full autonomy. And if something goes wrong, if the ship breaks down, if the crew gets sick, if the planet turns out to be unsuitable, help will never come. You are alone in the abyss, cut off from home by light years and decades. This is a psychological burden that is hard even to imagine. The crew must be ready never to see Earth again, never to return, to become exiles by their own choice, colonists in the absolute sense of the word. How many people are ready for this? How many civilizations will find volunteers for such a mission? And that is only the technological side. There is also the economic one. An interstellar ship is an incredibly expensive project. We are talking about trillions of dollars in modern prices, possibly dozens of trillions. The resources of an entire planet directed toward building one ship for a handful of people. What civilization can afford this? What society will decide to invest such resources in a project, the results of which will be seen by neither the current nor the next generation? Only a very rich, very stable, very long-term thinking civilization. There are probably few such. Most civilizations likely face more pressing problems: resources, energy, climate, conflicts. Interstellar expansion takes a back seat and remains a dream, not a reality. And if we talk about radio communication, suppose flights are impossible, but signals? We send radio waves that move at the speed of light. Probably civilizations communicate without meeting physically. The problem is that radio signals disperse. The further from the source, the weaker the signal becomes. After a few light years, our most powerful transmissions become indistinguishable from cosmic noise. To send a signal that can be received at a distance of thousands of light years, incredible power or an incredibly focused beam is needed, or both. Again, huge energy costs. And for what? To send a message, the answer to which will come in thousands of years. A conversation where a generation passes between lines. What is the point of such communication? What information can be transmitted? What relationships can be built? Perhaps that is why civilizations simply do not bother. Interstellar communication exists theoretically, but is practically useless. Too slow, too expensive, too inefficient. It is better to focus on your own planetary system. Colonize moons, asteroids, the nearest planets, build a flourishing local civilization, and forget about the stars. Too far, too complex, too expensive. This explanation of the Fermi Paradox does not require filters or uniqueness, just physics and economics. Interstellar distances are so vast that overcoming them makes no sense. Civilizations exist, there may be many of them, but they are all locked in their own planetary systems. Neither out of fear nor out of ethics, simply because expansion beyond limits is not justified. Space is too large, technologies are insufficiently developed, and resources are limited. And every civilization comes to the same conclusion. It is better to equip your own home than to waste effort on unreachable stars. But humanity does not give up. We continue to search. We build radio telescopes, analyze signals, and hope that someday we will hear a voice from the depths of space. And these searches have been going on for more than 70 years. The program for the search for extraterrestrial intelligence, known as SETI, has become one of the most ambitious scientific projects of humanity and one of the most disappointing, because in all this time we have found nothing, absolutely nothing. The SETI project began in 1959, when physicists Giuseppe Cocconi and Philip Morrison published an article in the journal Nature. They showed that even with the technologies of that time, it was possible to detect radio signals from a civilization of approximately our level of development if it was not too far away. A year later, astronomer Frank Drake conducted the first experiment, Project Ozma. He pointed a radio telescope at two nearby sun-like stars, Epsilon Eridani and Tau Ceti, and listened. Several months of continuous observation, nothing, only cosmic noise. This was the first failure, but not the last. More than 70 years have passed since then. Technologies have become incomparably more powerful. Radio telescopes have grown in size and sensitivity. Computers have begun to process terabytes of data in search of anomalies. In 1999, the SETI at Home project was launched, a distributed computing initiative where millions of people around the world gave the free resources of their computers to analyze radio data. The most massive crowdsourced scientific project in history. Millions of participants, 20 years of work, 12 billion potential signals analyzed. The result is zero. Not a single confirmed signal of extraterrestrial origin. Of course, there were candidates. Strange spikes, anomalous patterns, unexplained signals, but upon rechecking, all of them turned out to be either interference or natural phenomena, or equipment errors. The most famous candidate was signal SHGB02 plus 14A, caught by the Arecibo Observatory. A narrow band signal that repeated several times, but when an attempt was made to confirm it using other telescopes, nothing happened. The signal disappeared. Most likely it was a hardware glitch or terrestrial interference accidentally reflected in such a way that it seemed extraterrestrial. In 2020, the SETI at Home project officially ended. Enough data has been accumulated. Analysis continues, but new observations have ceased. The Arecibo Observatory, which was the main source of data, closed, and its telescope collapsed. An era has ended, and the outcome is sad. The cosmos is silent. Now a new project called COSMIC has been launched, using a system of 27 radio telescopes of the Very Large Array in New Mexico. It promises to expand the search hundreds of times, cover 80% of the sky, and listen to millions of stellar systems. But so far, the results are the same. Silence. Some scientists are already suggesting giving up on SETI. Too many resources have been spent without result. Suppose it is better to direct this money toward research that gives a practical output: astrophysics, cosmology, and exoplanetology. Others insist we have searched only a tiny part of the sky, only a narrow range of frequencies, only certain types of signals. The universe is huge. We need to search longer, wider, and deeper. But with every decade of silence, there is less optimism. It is not excluded that we are looking in the wrong place. Probably, intelligent civilizations use not radio waves but something else: laser pulses, gravitational waves, neutrinos, quantum entanglement, something we do not even guess. Or radio communication is a primitive technology used only by young civilizations like ours, and those who are older long ago switched to more effective methods. And we are trying to catch a signal of an outdated technology that no one uses anymore. Polish science fiction writer Stanislaw Lem proposed the concept of a contact window. The idea is simple. Each civilization passes through a short period when it actively uses radio waves for communication and radiates signals into space. For humanity, this window opened approximately in the middle of the 20th century when we invented radio and began to build powerful transmitters. But already now, we are gradually moving toward technologies that radiate less: cable communication, fiber optics, and directional transmissions. In 100 years, Earth may become almost invisible in the radio range. We will use radio only inside the planetary system, and even then in limited volumes. The window will close. According to Lem's estimates, this window may last only from 300 to 500 years, a tiny gap by cosmic standards. And if all civilizations pass through this window, if everyone starts with radio and quickly transitions to something else, then the probability of catching a signal is catastrophically small. It is necessary for two civilizations to be in the contact window simultaneously, for the distance between them not to be too large, for them to be looking in the right direction, for the frequencies to match, and for the signal to be powerful enough. Too many conditions, too little time. The windows simply do not intersect. This explains not only the absence of signals, but also the absence of visible artifacts. If civilizations quickly pass through the technological phase visible from the outside and then become quiet, we may simply not catch the moment when they make noise. We look at a star where a civilization existed 1,000 years ago, actively building, radiating, and developing, but now it has already switched to hidden technologies, or died out, or went into virtuality, or simply decided not to expand into space. And we see an ordinary star. Nothing unusual, but in fact there is a whole world there, just invisible to us. The concept of the contact window is pessimistic. It says, even if there are many civilizations, we will not find them, simply because the windows do not coincide. We shout into the void, but no one listens, not because there is no one, but because we are late or arrive too early. Time is not synchronized. No, there is an even darker explanation for the silence of the cosmos, the one that no one wants to talk about, but everyone thinks about. What if the reason is not in technologies, not in distances, not in contact windows? What if simply all civilizations destroy themselves? What if self-destruction is not an exception, but a rule, an inevitable stage through which everyone passes, and we are next? Humanity now possesses technologies capable of wiping our civilization off the face of the earth. Nuclear weapons, biological weapons, chemical weapons. Soon, perhaps, artificial intelligence that gets out of control will be added to this list. Nanotechnologies capable of turning the planet into gray goo of self-replicating robots. Genetic engineering that can create uncontrollable pandemics. Ecological collapse from uncontrolled use of resources. The list is long and frightening. We live in an era when, for the first time in history, humanity is capable of destroying itself, not from natural disasters, not from asteroids or supervolcano eruptions, but from its own technologies, from its own mind, which created tools of destruction faster than the wisdom to control them. The Cold War showed how close we came to the edge. At some point, humanity had enough nuclear warheads to destroy the civilization several times over. The doctrine of mutually assured destruction kept the world on the brink. One miscalculation, one mistake, one paranoid leader, and that is it. We survived. But there were several moments when the world balanced on a knife's edge. The Cuban Missile Crisis, an incident with an early warning satellite that took the reflection of the moon for a rocket launch. A submarine during the blockade of Cuba, where an officer refused to launch a nuclear torpedo. Each time, someone made the right decision at the last second. But what if next time there is no luck? What if the next crisis ends differently? And that is only nuclear weapons, a 70-year-old technology. And what will happen in 50 years, in 100? What other ways of self-destruction will we invent? Artificial intelligence surpassing the human mind may decide that people are no longer needed, or simply optimize something so effectively that the disappearance of humanity will be a side effect. Biotechnologies can create a pathogen against which there is no protection. A climate catastrophe can turn Earth into Venus, a planet with a surface temperature that melts lead. An ecosystem collapse can destroy the food chains on which agriculture depends. The options are endless, and they are all the result of progress. The more developed a civilization is, the more powerful tools it has, and the easier these tools can be used incorrectly, accidentally, or intentionally. Likely, this is the great filter, not in the past, but in the future. The moment when a civilization reaches a technological level that allows self-destruction. And most do not pass this moment. They destroy themselves in wars, disasters, and uncontrolled technologies. Only those who are wise enough, cautious enough, and united enough survive. But such are the minority. The majority perish, and the cosmos is silent because it is filled with the ruins of civilizations that could not cope with their own power. This is the most pessimistic explanation of the Fermi Paradox and the most frightening, because it means our future is in question. We are in danger, and the danger does not come from outside. It is within us, in our aggression, in our greed, in our inability to think long-term, in our tendency toward conflict and unwillingness to cooperate. Every war, every crisis, every catastrophe is a rehearsal for the finale, and one day the rehearsal may become the final performance. Carl Sagan used the Drake equation as a warning. He said, "Look at the last parameter, the lifespan of a civilization. Everything depends on it. All other factors may be high, but if civilizations live short lives, if they self-destruct 100, 200, or 500 years after reaching a technological level, then there are almost none at any given moment. The universe may be full of dead civilizations, planets where there once were cities, arts, science, and dreams, and now there is only radioactive ash and silence. Our task," Sagan said, "is not to repeat their mistake, but to survive, learn to control technologies, unite as a species, and solve global problems. And then, perhaps, we will become one of the few who break through the filter, who prove that intelligence can be wise, that civilization can be stable, and that a future is possible. But even if we survive all threats, even if we build a sustainable civilization, there is another factor working against contact: time. Time on a cosmic scale does not work in our favor. The universe is about 14 billion years old, the Milky Way more than 13 billion, and the Earth 4.5 billion. Humanity in its modern form has existed for several 100,000 years. Technological civilization for less than 200 years. We are incredibly young by cosmic standards, infants just born. And we look into space and say, where is everybody? But the question is not where, but when. Civilizations likely exist, but we do not coincide with them in time. Some were millions of years ago, others will appear millions of years later. No, right now, in this specific moment of cosmic history, we are alone. Imagine the galaxy as a huge city. Millions of people live in this city, but each person exists for only one day. In the morning they are born, in the evening they die. What is the probability that two people will meet? It depends on how many people live simultaneously. If at any moment there are only 10 people out of millions in the city, the probability of a meeting is negligible. The city seems empty, although millions have passed through it. The same is true for civilizations. If their lifespan is short compared to the lifespan of the galaxy, they simply do not intersect. They exist in different eras. The Milky Way may be home to millions of civilizations throughout history, but at any specific moment, there are only a few, or even just one, us. And we look at the empty sky, not knowing that 1,000 years ago, someone else also looked from another planet and saw the same void. And in 1,000 years, someone else will be looking and also will not see us. This time factor is exacerbated by the speed of light. Even if a civilization exists now at a distance of 1,000 light years from us, we see it as it was 1,000 years ago. Likely, 1,000 years ago they were at the peak of development, building megastructures and radiating powerful signals. But the signal has not yet reached us. We look at their star and see an ordinary star because we are looking into the past, and by the time their signal reaches Earth, humanity may no longer exist, or we will no longer be listening to the radio. The windows again will not coincide, only now not in space, but in time. And this is not just a hypothesis. It is a mathematical reality related to the finiteness of the speed of light. The universe is not synchronized. Each point sees other points with a delay, and the further away, the greater the delay. We never see the cosmos as it is right now. We always see the past, more or less distant. Perhaps that is why the cosmos is silent, not because there is no civilization, but because time does not coincide. We search for those who have already disappeared or those who have not yet appeared. We exist in different eras, separated by light years and signal delays, and contact, which seems so natural and obvious, actually requires an incredible coincidence not only in space, but also in time. Two civilizations must exist simultaneously, at a distance not too great, in a period when both use detectable technologies and both must be looking in the right direction. The probability of this is extremely small, perhaps so small that in the entire history of the galaxy, it happens only a few times or not at all. There is another possibility that we rarely consider. Suppose life in the universe takes form so different from ours that we are simply not capable of recognizing it. We search for carbon-based life because we are carbon-based ourselves. We search for water because we need water. We search for oxygen because we breathe oxygen. But chemistry is richer. Silicon, like carbon, can form long chains of molecules. Theoretically, life based on silicon instead of carbon is possible. It will be slower because silicon bonds are stronger and harder to break, but it is possible. Liquid methane or ammonia could play the role of a solvent instead of water. On Titan, a moon of Saturn, there are entire seas of liquid methane. Likely, organisms swimming there use methane as we use water. We will not see them because we do not know what they should look like. And what if life can exist in even more exotic forms? In the atmospheres of gas giants, organisms the size of continents, floating in clouds of hydrogen and helium, feeding on the energy of lightning, or in the interiors of neutron stars, structures made of nuclear matter living on timescales of milliseconds, or in interstellar clouds, slow, huge, thinking over millennia, or even in the very fabric of space-time. Quantum fluctuations organized into something we cannot call life, but which possesses complexity and perhaps intelligence. We look at the cosmos with eyes tuned to see only what looks like us. But if life has taken other forms, if intelligence has evolved along other paths, we could be looking directly at it and not understand that it is life. It is as if an ant were trying to recognize a human. It sees a giant moving something, but does not understand that it is an intelligent being. The scales do not match, the criteria do not fit. So we may be passing by intelligence that exists on other scales, in other environments, according to other laws. Likely, that is why the cosmos is silent, not because there is no intelligence, but because we simply do not know how to recognize it. We listen to radio waves, while they communicate with gravitational waves. We search for planets, while they live in stars. We measure time in seconds, while they think in eons. A mismatch not in space and not in time, but a mismatch in nature itself. They are so different that contact is impossible even theoretically, not because of distances, not because of technologies, but because we exist in different realities. We intersect physically, but do not understand each other. This is a comforting thought in a sense. The cosmos is not empty. It is full of life. It is just that this life is so diverse that we see only a tiny part of it, the part that looks like us, while the rest remains invisible, hidden not out of malice or fear, but simply because we are looking with the wrong eyes. But let us return to more down-to-earth explanations. There is another reason why we might not see traces of interstellar civilizations. Suppose colonization of the galaxy simply does not happen, not because it is impossible, but because it is impractical. We imagine a highly developed civilization as something expansive, building stellar empires, colonizing planets, spreading across the galaxy. But why? For what? If you have technologies that allow for full control of your planetary system, why fly to other stars? On the asteroids and moons of your system, there are enough resources for millions of years. The energy of the star is practically infinite by human standards. The space for growth is huge. Orbital stations, rings around planets, clouds of megastructures. Why risk an interstellar flight when everything necessary is at home? Moreover, by the time a civilization reaches a technological level allowing interstellar flights, it likely already has virtual reality indistinguishable from the real thing. Why fly to other worlds if you can create any world inside a computer? The entire universe, as you want to see it, is available without the danger and expense of actual travel. Suppose developed civilizations simply go inward, into virtual worlds, into simulations, into digital existence. There, possibilities are infinite. Instantaneous communication, no physical limitations. And the physical cosmos remains empty and silent. Not because there is no one there, but because everyone who could master it chose another path, an internal rather than an external one. This would explain why we see no traces of colonization. Civilizations reach a certain level and stop. They do not perish. They do not hide. They simply lose interest in the physical cosmos and transition to another form of existence. And the galaxy remains quiet, filled with stars and planets around which silent civilizations revolve, living in their own digital worlds. Or even simpler, likely interstellar colonization is indeed impossible for most civilizations for economic reasons. Too expensive, too risky, too long. Sending a ship to another star is an investment that will pay off in a century or a millennium. What society is capable of such long-term planning? On Earth, we struggle to plan a decade ahead. Politicians think about the next elections, business about quarterly reports. Long-term projects are poorly funded because the results will be seen by other people, other generations. And an interstellar flight is the extreme degree of long-termism. You invest resources, and the result will be seen by your great-grandchildren or their great-grandchildren, or no one at all if something goes wrong. Few societies are ready for this, perhaps none at all, and therefore civilizations remain tied to their stars. Neither out of fear, nor ethics, nor technological impossibility, but simply out of economic impracticality. Now let us imagine the incredible. Imagine that tomorrow we receive a signal, an unambiguous, undeniable, clearly artificial signal from the depths of space. What will happen? First, shock. Absolute, worldwide shock. We are not alone. Proven. All religions, all philosophies, all ideas about our place in the cosmos will have to be reviewed. We are no longer unique, not special, not chosen. We are one of many forms of life in the universe. For some, it will be a liberation. For others, a collapse of their worldview. Second, questions. Thousands of questions. Who are they? How developed are they? Where are they? Are they friendly? What do they want? Can we understand their message? Should we answer? And if so, what to say? Who will speak on behalf of humanity? What government? What organization? What person has the right to answer a message that may determine the fate of our species? Third, panic. Inevitable panic among part of the population. Conspiracy theories will flourish. Some will shout that it is a deception, others that it is an invasion. Still others that governments have hidden contact for decades. Social networks will explode, the economy may stumble, people will start acting irrationally, buying up food, preparing for the apocalypse. Some religious groups may perceive contact as a sign of the end of the world. Fourth, hope. Huge, incredible hope for another part of humanity. Finally, we are not alone. Is there someone else looking at the stars and asking the same questions? Perhaps they will help us. Share technologies, knowledge, wisdom, solve our problems, teach us to avoid the mistakes they have already made. This hope may be naive, but it will be strong. Fifth, slow realization of reality. They are at a distance of hundreds or thousands of light years. The signal took centuries. Our answer will take centuries back. The conversation will last generations. Each question and answer is a century of waiting. No instant help, no quick decisions. Only a slow, incredibly slow exchange of information. What can we transmit? Mathematics, physics, chemistry, this is universal. Information about our biology, history, culture, questions about them, and then wait. Wait until the answer comes. Perhaps those who sent the message will not wait for the answer, but their grandchildren will receive it, and humanity will change not immediately, not quickly, but fundamentally. We will know that a goal exists, a contact, a connection. We are part of something greater. Or contact will turn out to be a disappointment. We will receive a signal, understand it is artificial, but not be able to decipher it. Too different, too alien. Their mathematics is not like ours. Their logic is unfathomable. Their message is just noise to us, though clearly structured. We will know someone is out there, but we will not be able to communicate. We saw, but did not understand. We heard, but did not make it out. And this could be worse than silence. Knowing someone is nearby but being unable to establish contact is a special form of loneliness. Or even worse. The signal turns out to be old. We decipher it and realize the civilization existed thousands of years ago. It sent a message into space, hoping for an answer. But by the time we received it, they were gone. Died out, destroyed themselves, disappeared. And their signal is the echo of a dead civilization, a ghost in the night. We are alone again. Now we know that once we were not alone, and this knowledge may be even heavier. So what does all this mean? Each hypothesis gives its own answer. Rare Earth says, "We are a rarity. Take care of yourselves." The Great Filter warns, "Danger is ahead. Be cautious." The Dark Forest advises, "Remain silent and hide." The Zoo promises, "Become better, and they will reveal themselves." No, most likely, the truth is somewhere in the middle. The cosmos is silent for many reasons simultaneously. Life is rare, distances are vast, time is unsynchronized, civilizations perish or simply see no point in expansion. The Fermi Paradox is a mirror. We ask where everyone is, but we are actually asking about ourselves. Who are we? Are we alone? Will we survive? Do we have a future? And the silence of the cosmos teaches us the main thing. We live in a unique moment in history when for the first time we are capable of asking these questions and seeking answers, capable of understanding the scales of the universe and our place in it. This is a privilege and a responsibility simultaneously. And perhaps the meaning is not in finding the answer, but in searching. Not in meeting brothers in intelligence, but in becoming worthy of such a meeting. The Fermi Paradox will remain with us until we find extraterrestrial life, or understand why it is not there, or until we disappear ourselves. But while we are here, while the search goes on, the question is alive, and therefore hope is alive.